when I say AA, which means both are measuring at the same angle, and this is not very interesting for this experiment because it is highly predictable, because you are measuring the complementary quantities both at the same angle. At some point, at one end you will receive plus of, and at the other end you will definitely receive minus
So
of.
what the value would be
That's
2, right?
trivial.
What is the value will be then? Is it 2?
What?
What is the value will be then of the function
So-
of that time? Is it 2 or?
Okay, I think I understand. So when they calculate this joint detection, they actually measure the expected intensity.
So
Alright?
it's sort of average, right? Not exactly one observation. Sort of a lot of observation. in
You
the
can think
angle
about a
and-
normalized value, yes. I think it's just probability.
Yeah,
You
probably.
just say like you
Just
measure the
random
intensity,
quantity.
right?
Yeah,
If you measure the
It's-
intensity,
it's a
you
joint
lost the
problem.
And there
phase.
is measurement.
And
I'm
if,
sorry?
so there has to
if you measure the intensity,
Yeah.
you lost the phase. If
Okay.
you lost the phase, you lost the polarization reading.
well,
How do you measure the field?
what they do is, here intensity is related to the count of photon.
Yes.
Alright? And
Okay.
when you count the photon, you actually know the polarization of the photon, because if the incoming photon is vertically polarized and your polarizer is at the zero angle, you don't receive a photon. So that's how you actually
So-
retrieve the information of polarization.
So, so one way to explain is that you put a gamma ray
Yeah.
to a neutron, you get 2 electrons,
You put a gamma ray to what?
a neutron,
Neutron. Okay.
and then you get 2 electron in a different spin, right?
Are they entangled?
They are entangled.
Okay.
So what happens is like you have 2 setup.
Mhm.
One is like TE, other is TM, right? And whatever you receive here, you measure the intensity. You assume that that's TE. There is
Are those like single electrons,
yes.
or
It should be single.
no? I mean like for each. So when you shoot the gamma ray, is it like shooting one photon at a time, or it's a beam?
It's a beam. It's a beam.
When you say about beam, it will not happen here. Here we are all these are single photon physics, not beam physics.
Okay. So thing is that based on your setup,
Yeah.
you can only say like whether you're receiving TE or TM. But sometimes you have both T and TM, like QTE or QTM.
Depending on your measuring setup.
Um,
Yeah, because if the incoming photon is in, say, for example, horizontal polarization, but your polarizer is at 45-degree angle, 50% of the time you will receive, horizontal polarization, and 50% of the time you will receive vertical.
okay, in that case, how do you know that you're receiving, like this moment you're receiving TE and the other moment you're receiving
Because
TM?
none of these angles are 45 degrees. They are 22.5 degrees, something which is biased. So when you bias the measurement, then you have some polarization with higher probability. And that's what it is interesting here.
My point is like you lost the polarization info.
No,
Wait,
because here polarization of a single photon is related to the detection of that photon. So if
But
you detect
detection
it, you know the
methodology.
polarization.
okay. So detection setup
It
will
is true
define.
for beam physics, but the polarization of a single photon is related to its detection because you have the polarizer. So whenever it passes through, you detect it, and when you detect it, because of the polarizer settings is done by you, you know the polarization of the photon.
Yeah. Okay.
So,
And another thing is that how do you correlate the spin and the polarization?
I'm not correlating spin and polarization. These are two different experiments.
Oh,
okay.
Either you do the spin or you do the polarization. If you do
Okay.
the spin, it is about electron. If you do the polarization, it is about photon. These are two different experiments.
Yeah, I
It's your
get confused
choice.
with that. Like you're
my
talking
bad.
about spin and then
Yeah, that's my
you
bad.
move to
I have a
polarization.
Yes.
So for a single photon, if your photon is polarized like 45-degree angle,
Yeah.
and if your detector is like 90-degree angle, so
If your detector, so the photon is 45 degree, and it going towards this, and the polarizer is 90 degree,
90 degree.
which means, yes,
So can the detector detect the polarizer photon?
so this is the photon, this is the detector.
Yeah.
So you say that what will the result of the detector?
Yeah.
50% of the time it will pass through, 50% of the time it will not pass through. Because, so if you take the average, you will receive photons with, average means like classically, total, take the total number, you will receive the beam with half of the original intensity.
Yeah, because I
Yeah.
understand. So is the 50% time it can detect?
Yes.
Why 50%?
Which means it passes through. What is that? 50% why?
Why?
Not 50%, it depends on angle, like it's 65 degrees, so most of the time it's detected particle and less.
No, I mean, he's talking not 65 degree, 45 degree. Are you talking about 45 degree? Yes, he said.
I told for 45, I did not
Yeah.
know 65.
Yeah, what is, now what is the question?
And why 50%?
Because it's
For the
45.
vector product, I'm sorry, the inner product of the vectors. When you say the polarization of photon, you are actually doing a vector thing, right? And I mean, when you take the inner product for the angular deviation of two vectors, which is 45 degrees.
So you mean you told that it's a big vector product and it is square, right? Vector product is square. 45 to 1 by root over 2 and 1.
Oh,
So that should be
square because of the probability, yes.
Yeah.
Yeah.
Okay, so every time when you try to measure the probability is like angle and their vector product and there is
Cos
square,
of
right?
angle, cos of angle,
Yeah,
because
cos
of
of
the
angle.
angle.
Yeah, is it because like
Right.
45 degree means superposition up to 90 degree. If it is this way, you cannot detect. If this way, you can detect. And if it is row AA, suppose one gets the signal, then it has, I mean, if it exactly same angle, then other cannot, of course, right? Because it's opposite.
And I think
But it is like single photon basis, so for single photon, you are not saying that it is either passing through or not passing through the polarizer. You are saying that because of the quantum mechanics, it is at the same time passing through and not passing through the
With
polarizer.
probability.
That's quantum mechanics. At the same time, it is going through or it is entering the door and not entering the door. That's quantum mechanics, yes.
yeah. Yeah. And another question is like, I think the intensity will be changed when the detector will detect, right?
Yeah. I actually have this set up in my desk. I mean, I have like 3 polarizers, and if you shoot the
Yeah.
laser beam, and if you take the 2 polarizers and
Yeah,
at
I
the
know,
45 degree,
yeah,
you will see it.
If you
Yeah.
go for microscope,
Yeah.
if you change polarizer, then
Yeah. Actually, I have this
yeah.
video in my Facebook profile. You can just
Yeah,
check it.
I know.
I think I didn't answer to your question.
Oh, sorry.
Row AA, I think I got the answer because
Okay.
I forgot. Each sample sort of, if you detect it here, you cannot detect it because you detect with
Yeah.
light.
Mhm.
So,
I think I didn't answer to his question, too, right?
So A mean, so A prime all in left side and B prime all in right side, right? Like A is Alisa and B is Bob.
Yeah, Alice, Bob, Alice, Bob, Alice, Bob.
So what is like when it's like row of A and B. So what is the value? Like
For CHSH
so
experiment,
A
it was,
is
I think,
0 degree, I
22.5
think.
degree.
A is 0 degree and
I
A
think
prime
it
is
was
90.
like 0, 22.5, 135 and something else. I don't remember.
no, there's two value in one side. One is A, another is A prime. So if A is at 0 degree, so because in picture there shows two angle. One is Z of A, another is X of A.
Yeah.
So I think A is at 0 degree and A prime at that 90 degree. And B
let me
is
check.
at 0 degree in this side and B prime in that, like in 90 degree.
No,
Okay.
none of those angles were 90 degrees. It is, I think, 0, 22.5 and 2 other, I can't remember. Because if you measure it at 90 degree, you are actually entering only one of the states. You have to have a biased measurement to have it in superposition. And if you don't have it in superposition, you can't actually test entangled states. Let's take rest of the question after the talk. But I understand because when I started with photons, I didn't even explain that we are talking about vectors, and now these results are coming from not even direct physics, it is coming from directly quantum optics. So that's a huge quantum leap. And I didn't discuss any of those ideas between these two. And these two ideas took like 50 years of development in science. So it is pretty reasonable that there might be confusions. What I skipped is like 50 years of development. So, but the catch of this slide is that it is when you do it in the lab, this is true. This is true, yes. And Bell inequality is violated. So let's think about the.
So what's the value of rho AV maximum?
What is that?
What's the range rho? Of AV?
Rho for joint detection it is 2.
0 to 2.
0.
Minus 2 to
The
2.
lowest thing, no, it's minus 2 to 2. I remember. I mean, I did this course like 1 year back, but I think it is minus 2 to 2. So far I remember. I can always look it up from the literature. Dr. Shee's book is also here. So okay. So it is the game of photon is the CHSH game for photons, not electrons. All right. Again, the photons can just a recap of the basic assumptions of quantum mechanics. That photons can be either horizontally or vertically polarized. Actually, it is not either. That's a typo. It can be either horizontally or vertically polarized, or in both states at the same time. You remember that the photon is at the same time entering the door and not entering the door. That's the both or superposition. And the second for the rule of the game is that when you measure the polarization, if they are in equal polarization, it randomly collapses into one of the two states. T is random, and that freaks lots of people. For this game, 0 means, sometimes I will use numbers, so 0 means horizontal polarization and 1 means vertical polarization. Two numbers mean 2 photon, which means when I say 1, 1, it means this photon is horizontally polarized at Perthes end, this photon is vertically polarized at Perthes end, this is vertically polarized at Nilabjas end. When 0, 0, horizontally polarized at Perthes end, vertically polarized at Nilabjas end. So then a plus sign means superposition. So what if I say 0, 0 plus 1, 1, which means this one is Perthes, this one is Nilabja. So at Perthes end, the photon is at the same time horizontal and vertically polarized. At Nilabjas end, the photon is at the same time horizontal and vertically polarized. The plus sign means superposition. Once again, I am like making lots of quantum loops. So this is the game of photon, or the CHSH game. So we were talking about creating entangled photons. This is the part. This is quantum mechanics here. These are not quantum mechanics. Yes.
Can you explain what is entangled?
What is entangled?
Entangled photon. You just said entangled.
Oh, entangled photon. Oh, okay. So he asked, what is entangled photon? Entangled photon means for two photons. Entangled photon means a pair of photons for which some particular quantity of both the photons are really entangled, which means like really complemented by each other. So, for example, if I say that for an entangled pair of photons, the polarization is entangled, that means if the polarization at one end is horizontal, at the other end of the photon, the polarization has to be vertical. Has to be because of the. Oh, I think you missed that part. So because of the it is related to the law of the conservation of momentum and energy.
Entangled photon is the law of momentum.
Think about from this perspective. When you say the polarization of a photon, it is related to the angular momentum, right? And the angular momentum of a closed system is always conserved.
I read about the entangled photon is like that. If you change one photon like properties here,
Yeah.
maybe like 200 meters apart from another photon.
Or at the other end of the
A
universe.
universe, the photon change also. His what is
Yes,
the
so what are you
complementary.
changing? What are you changing? Say for example you are changing the polarization, which means if the photon at one end, if you set it to horizontal polarization, at the other end, no matter how far it is, it has to be in the vertical polarization. You said one thing, you change one thing. So I'm picking horizontal, I'm picking polarization. Now, how polarization is related to the photon? Polarization is related to the angular momentum of the photon. And angular momentum of a closed system is conserved. So that's where the law of conservation comes into play. Yes.
I think I'll ask it after the presentation because polarization you may not be able to change.
What is it?
Doing, like changing one polarization,
Yeah.
you can change the spin
Yeah.
of electron
Yeah.
and you can influence the spin of the other electron,
Yeah.
entangle.
Yeah.
But polarization, I'm a little bit confused about that.
Yeah,
you may not be
understand.
able to do that.
Because what you're asking is like 80 years old question. So when the moon is on the other side and if you are not looking at the moon, is it really there? This is the question asked by Einstein. So what I said is really confusing because this question splits the philosophers in two different groups. It's about the reality. Is this table really here? If I don't look at it, if I don't touch it, is it really there? So what defines the reality? Is it the observation or it has an independent and its own existence? So that's why it like pissed you off, I know.
No, it didn't piss me off, but thing is that,
It pissed lots of people off. Right. So
like classically we change the polarization in a way,
so,
so it doesn't go in the
yeah, I
same way.
understand, I understand.
Okay.
Alright. So, okay, here's the game. So you can see that's the winning condition. A XOR B. So which is nothing but just a summation for binary numbers. A XOR B equals to S wedge T. This is nothing but multiplication for binary number. So the referee sends 0 or 1, these are all 0 or 1, S, T, A, B. Sends 0 or 1 to Partha and 0 or 1 to Nilabjo. And they don't have any standard communication like phones, cell phones. They can't visit each other. So which means like whenever we all are in their vicinity, they can communicate. So that's what. So this is the setup, and they are replying A and B to the referee, and the referee evaluates that predicate, and if it is equal, he says that they win, right? I mean they're entangled, so they have to like win, right, together. So
So how you know that they are two are entangled?
we don't know yet. We assume that they may have a shared entangled photon pairs.
Okay.
That's the assumption.
Assumption of the plate. So actually, can you actually build like any system like that?
Yeah.
You can build, right?
Yeah, they do it all the time in physics lab.
Physics
They
lab.
have two different groups. They do it all the time.
Yeah.
Let's go. Okay. If you Google it with SPDC, this was invented by UMS person. This is the technique how they make this entangled pairs.
Entangled pair.
There are other techniques, but this is the most popular technique. Okay, so this is the real game, a CHSH game or game of photon. Think about this time. So they don't have any entangled pair. So there is no quantum mechanical system between them. So they are not using any quantum mechanical advantage. So in that case, at best, they will win 75% of the time, which is related to the Bell inequality. I said Bell inequality is the maximum level a classical system can achieve. So if there is no quantum mechanics, if you want to derive it, it's easy. You just draw a table, right? Partha, Nilabja, it's like 0, 0, 0, 1, 1, 0, 1, 1. Standard truth table. So without a quantum mechanical system between them,
Why the equation is like A?
the predicate, yes.
A XOR B equals to.
Why is it this? Okay.
No,
This
because
was-
is left and right hand side should have the same operation. because you said the referee sent A and B,
Okay.
A sent T,
Okay.
and he is receiving A and B.
Yeah.
But
Yes.
after two different operations, if they are saying
Okay,
No,
okay.
anytime if you win, it's one, right? So if Nilabju wins or Parthu wins, the referee will get one. So it's
No,
75%
referee
always.
is send, checking what he sent and what he received. If this is same,
The
then
referee can send either this pair or this pair or this pair or this pair.
yeah.
This is S and T, S and T.
Okay.
All right.
And what referee will check?
Okay. What?
So what the head sign means? The is head P.
Oh, the and. This is and. I said in binary algebra, this is just multiplication.
Okay. So one is and in left side is XOR.
XOR in binary algebra, this is single bit binary algebra. This is just summation, addition, nothing else. In single bit binary algebra.
And means actually
Multiplication. Yeah,
So
in single bit binary algebra.
yeah. So why is referee comparing the input sum of input equal to multiplication of output?
Why?
Yeah.
He is the referee. He defines the rule for winning the game. He is the Lannister, the senior most
No,
Lannister.
he can check like what he sent. If he get the same thing back, then
So how is
That's
S-
another game. That's another game. The CHSH game is imagined by this guy called K. And he thought this is the predicate which can actually differentiate between the winning strategy of classical system and winning strategy of quantum
so
system.
then how it's become 75%?
Okay, so let's do it.
Okay.
So 75% is the maximum.
Yeah. So 001 first to the S&P.
Yeah, sure.
So the result will be the left hand side will be like
Not yet, not yet. We are talking about a game, so we have to decide the strategy first. So what is the strategy? There could be more than one strategies. Strategy number one. Whatever comes, always send one. Strategy number two. Whatever comes, always send, zero. Strategy number three. Whatever comes, send a random bit. So it could be either 0 or 1 with equal probability distribution. Okay.
It's maximum sum.
And again, when Partha is choosing these strategies, Nilabju could be choosing either this or this or this. If
another can be like if you get one send 0 like invert.
yeah, that's what he's saying.
No, it's
Oh, always
send-
invert, negate, yeah.
Yeah.
Always negate. Alright? So say Partha is choosing this. Nilabju has the liberty because they are not communicating each other because we are in the vicinity. So Partha is, if Partha choose this one, Nilabju has the liberty to choose either this or this or this or this. So, and for different strategy, you will have different percentage of winning probability. But if you work out all of them, you can at best have 75%.
Actually, yeah, you can.
It's standard algebra. Yes.
Can you just like with
One-
get
one strategy?
with probability p and 1 minus p, and you can optimize it over p, right?
Yeah.
Then you can like
Yeah.
get something.
Yeah.
Like that.
So, do you want to test one of them and see the probability? I can go ahead if we. I don't know if how much time we have. We are almost done with the.
No, if you choose only one, it should be less than 75. But how you like? I mean, just how you get the like 75?
At
highest?
best?
Yeah.
Oh,
Because if you choose randomly 2, it will be less than 75.
yeah. I mean, those are like standard literatures. You just Google it. They will say that for this probability you will have this percentage. But these are like well understood algebra. Is probably. But I understand. I mean, you really want to work it out, we can do it. But when we do this, again, I'm skipping lots of stuff. So when we have some quantum mechanics playing in between Earth and Nilabjo, something which is not well understood, something which is there and not there at the same time, something we watch every evening, and then the percentage of winning is 85%. You can't beat this limit. That's the result of CHSH inequality.
No, it's not obvious, like, now you exchanging information, so the percentage should be higher.
I'm not exchanging information. I'm sharing a quantum resource between the. When you say information, you are talking about Shannon entropy and stuffs.
But if
It could be defined, but it's yes, but I mean it's not exactly. Well, yeah. I mean you can say that use the term information.
But
Yes.
if you entangle them, or if you send some information, then there is some correlation like in the output, like A and B. Then the percentage should be increased, like 75 to 85.
Yeah, it increased.
Yes, like so.
No,
What's the
how is it? How
the
they are-
exciting thing? Yes, it's
Oh.
not obvious.
That's the best question. Yes.
How are they
The exciting
implementing
thing is that, I mean, for, in 2004, it was exciting because before then, in game theory, 75% was the highest limit. So this result came out in 2004. So in 2004, it was exciting. In 2014, it isn't that much exciting. It's true.
No, now if you communicate perfectly, then the percentage will be 100%.
That's the assumption. No one can communicate. It's a non-local game. No one can, I say, we are in the vicinity. It's not only you two. So you can't.
Can you just show how the entanglement is
I'm sorry?
used in the game? I mean, how it is increasing? Why?
Why? Okay, okay. I don't think I will be able to explain it in like in another. I mean, are you
It's
familiar
putting
with?
some constant like 0,
Okay,
0, 1,
okay.
1 by 2.
Let me just give you some sketch. When I say, oh, so they actually measure the photon on both ends, right? And how do they measure it? They use some observables, which are 4x4 matrices. And they, for each angle, which is A, B, A prime, and B prime, they use 4 different observables, or 4 different 4x4 matrices. So these angles are carefully chosen, these matrices are carefully chosen, and only for those conditions, the maximum probability is achieved. Otherwise, it might be 80%.
No, I mean, how it is
81%.
like applied on the S and T. I mean, they have like S and T are not entangled, right? These are just.
No, SNT are not entangled, yes.
So
they-
what is
They are thrown at them at random.
Yeah. So like they can measure entangled with under this inequality.
These are classical entities. These are
Yeah.
not quantum.
Yeah.
They are just 0
Now,
and 1.
like so, you will sort of use the entangle this operator on that thing, right? In some way. So
I'm using the entanglement to define A and B, not S and T.
okay.
If S and T are not entangled,
S and T are not even quantum. They are just numbers, 0 and 1, binary numbers.
then how you establish the correlation?
Correlation comes from the strategy